So the first example problem which we're going to look at, as you can see, is a simple cantilever beam with a tip load at the very end. And what you are asked to find the deflection at A and as well as the slope at A. Now we know that in this beam here, the deflection will be highest, and you can expect the value of the deflection you will get as a negative value, because here, say if you take this your positive y and your positive x, your beam goes vertically downwards. So let's go ahead and try to do this particular problem. I purposefully put the figure over here so that even if I scroll down, you will get to see the original figure and have a sense of what is going on. So if you take a look at this beam, and let's quickly draw for our convenience the cantilever over here. Remember that what we have already at our disposal is this relationship. So we essentially have to find the moment at how it varies along the length of the beam. So now here let's go ahead and mark the axis that we already just talked about. So I have my positive y-axis over here and the positive x-axis over here. Right, so let's go ahead and from this particular origin, let's write the expression for the moment at the different points along the length of the beam, which is very simple. It's going to have one standard expression here for this case. So to get the expression for the moment, for example, is using the method of section. So if we go ahead and draw a section, say at any distance x from here, and if you write the equilibrium of that particular section, what you have is something like this. So you have the beam where you have, this is your load P. Now at the right hand side of the section, I'm going to mark my positive shear and my positive bending moment that is there. Remember, the positive shear is the one which tries to rotate your beam in a clockwise manner. So this is my positive shear V, and the positive bending moment is the one which causes your beam to sag or your beam to smile. So this is my positive M and M over here. Now here I'm mostly concerned with this moment that is there, and I know that this distance is x. So from this one you will get the expression that m of x equals to minus p times x, that is there. So now I am going to go ahead and take this and plug this back over here, do the double integration. First find the expression for the slope, then find the expression for the deflection y, that is this. Let me go ahead and do that. So you see in this one I have integrated this once over here and I get this expression. So integration of minus px dx is minus px squared by 2 plus the constant of integration c1. You integrate it again, you get this guy over here. So now as you can see, we have to find our constants of integration c1 and c2 over here. Now how do we find that? Using the boundary conditions. Now here the boundary conditions can be what? So at this end B that you have over here, so that is at x equals to L, your slope is 0, because for the cantilever where the part that is fixed, you have the slope is 0, as well as the deflection y equals to 0. So we can use those two boundary conditions to find the constant c1 and c2. So let's go ahead and do that. These are the two boundary conditions at B, that is at the point B, that is at x equals to L. You have the rotation as 0, the slope as 0 over here, and you have the y of B that is equals to the deflection of the B equals to 0. So if you plug those two guys back over here, for example, if I plug the boundary condition 1, this one, into the first expression, you will get the value of the C. And after you get the value of the C, you put it back over here and you put this condition back in this expression, you will get the value of C2. So once you do that, the values of C1 and C2 that you will get, I'm not writing all the entire steps and details because this is very preliminary algebraic manipulations that you have to do. So what you will get after substituting in the equations, So these are the constants C1 and C2 that you get. So and once you have the constants, you can plug back in over here to write the expression for the slope and the expression for the deflection. So let's go ahead and do that. So once you have written out the expression for the slope and the deflection, see the problem asks you to find the deflection and the at the slope at A. So that means at A, we know that x equals to 0. So if we go to A over here, so here this particular point is x equals to 0. So if you put the value of x equals to 0 over here, you will get the value of the slope, that is theta at A, that is dy dx at A, and also the y at A. So let's go ahead and plug it to x equals to 0 and let's see the expressions that we get. So these are the two expressions that we get: PL square by 2EI, that is the slope at A, and minus PL cube by 3I. And as I said, as we said in the beginning, we expect a negative sign because we know it's the negative deflection. So let's, and the slope is positive. So let's go ahead and draw the deflected shape. Even if you don't have this from plain intuition, you can draw the deflected shape. So let's go ahead and draw the deflected shape and mark the points. So this is the deflection, and you will see that over time, as you keep on writing this equation, it becomes sort of ingrained in your memory that you have a cantilever with a tip load, the deflection works out to be PL cube by 3EI, and the slope is PL square by 2I. So slope is a positive slope and the deflection is negative because it goes vertically downwards over here. Now, one thing you would also want to check is that when you have these deflections that is there, that you can plug back the units of E, I, L cube. So you will see that this expression goes to the order of mm or inches or so on. And if you should also plug back into the expression of this one, to find the units of the slope of the rotation that you get over here, right? So I hope this problem example was clear. So in this one, we looked at a cantilever beam with a load at the tip. Let's go ahead and look at the second example. So the second example problem is a beam with a overhang, a simply supported beam with an overhang with a load P at the very end, and the dimensions are given overall. The first part of the problem, it asks you that for this overhanging beam to find the equation for the elastic curve. So it asks you to find the equation. So not in terms of the numbers, but just how y is a function of x. Also the, what is the maximum deflection, and remember all of this, and the last part it asks to evaluate after you plug in the numbers. Now all of this, it asks for just this portion AB, and there is a reason why, and you will later understand why it asks only for AB and not at the point C over here. So let's go ahead and start and doing this particular problem. So in this problem as well, if we go ahead and take a section somewhere over here, say at a distance x from the left end, and if you write the expression for the moments over there, now to write the expressions for the moment, you would need to find the reactions first. So this is already solved. I will write the reactions over here. You can go back and check it later. So these are the reactions that you get. So at the left end is minus P over L. So essentially it pulls the beam downwards over here, right? So now at a distance x, let's draw the free body diagram and write the expression for the moment. So this is the free body diagram of the beam. So I'm going to write the expression for the moment now. So now that I have an expression for the moment, I know my basic relationship, that is ei d square y by dx square equals to m of x. So I'm going to plug in that one over here, integrate it twice, first to find the expression for the slope and then the expression for the deflection. That will give me the equation for the elastic curve. So these are the two expressions that I got, first for the slope and then for the deflection. Now my boundary conditions are that, now remember, this expression for the moment is valid from x equals to 0 to x equals 12. So here maybe I go ahead and draw my axis. So this is my positive y and this is my positive x, and this expression is valid from x in 0 to L, that is over here. Right? So now, if now my boundary conditions, I have two unknowns, that there are two constants of integration. The boundary conditions are that since it is point, this is pinned over here and it's a roller over here, so the deflection at x equals to a, or at x equals to 0 equals to is 0, and at x equals to L also y equals to 0. So let's go ahead and write the boundary conditions. Now, once you use these two boundary conditions over here and you plug in both of this, so for and in this one, this equation doesn't yield anything. So for since you are dealing with the deflection y, you plug both this back in over here and you get the following values for the constants of integration c1 and c2. So now that we have the values of the constants of integration, I'm going to plug this back over here to find the equation for my elastic curve. So the first part asks you to derive the equation for the elastic curve. So that solves the first part, and then it says find the maximum deflection. So how do I find the maximum deflection? It is simple. Now that we have the expression for the deflection, and remember this is only for the place for the region AB. So this is valid only for the region AB, that is from x equals to 0 to L. So I'm going to differentiate it once and equate to 0. So that will give me the location x at where I in the beam where I can expect my deflection y in the region AB to be the maximum. So let's go ahead and take the derivative and equate it to 0, and let's see what is the point where in the region AB I have the maximum amount of deflection. So you get that at x equals to L over root 3, you are getting the maximum deflection. So if we go and plug this guy back in over here and plug in the other estimates that I have, that is L equals to 4.5 meter, E equals to 200 GPa, you are also given the second moment of the area, that is 300 raised to 6 mm raised to 4, and also the value of A that you see, which is given as 1.2, you will get the following number. So you see, this is get the value of the y max in the region AB, and it comes out as positive. So that means the deflection is in the upwards, and it's also obvious if you just go by simple intuition, if you are pushing it over here, the deflected shape of the beam would look something like this. And at x equals to L by root 3, which may be, somewhere over here in this region, you are getting this maximum deflection. So I hope this problem example was clear. So at x equals to, so maybe let me mark the distance. Right, so I hope this problem example was clear how we got this one. Now remember that, as I said, that this is valid, whatever we did is only for the portion AB. Now if you were dealing with BC, you see the expression for the moment would change. So then you have to go ahead and solve this for a different set of numbers, different sets of equations, and there is a problem later which tells you that how, because essentially you have a region of discontinuity, you have a point load over here, a region of discontinuity over here. So all these things are easy to do when you have no discontinuity, you have only one expression for the moment dependent on x from the left hand side over here. Now that this problem example is solved, now what I want you to do is you can go ahead and try solving this problem example, where maybe you have a simply supported beam with uniformly distributed, and say a length L. You will see for this one, if you go ahead and solve it, again just calculate the reactions here, start from the left end, you will see the deflection, and it's obvious here the deflection happens maximum at the center, and the value of the deflection, this is also a very standard problem which if you do several times it gets just ingrained in your memory, and for this case you will get the value of the maximum deflection as y max is 5 by 384. It will be negative because it happens down, WL raised to 4 divided by EI. So go ahead and try solving this problem and see that for this example if you get this expression or not. This is a problem example which has a discontinuity in the beam within itself, that at this point P and you have an applied load, and it asks you to find the slope and deflection at D, at exactly at that point. Now here you cannot do away with just writing one expression for the moment over here, because you are asked to find the slope of deflection exactly at the point of discontinuity over here. So here you have essentially two regions, region 1 from 0 to L over 4, and region 2 which is greater than L over 4 over here, that where you have to find out the expressions for the moments, and then as a consequence of that you will get four constants of integration, because they're dealing with two regions of the moments. We'll write the expression and you will see soon. So now the question is that how do we solve these kinds of problems where we have a discontinuity of the nature which you have in this expression over here. So let's first go ahead and write the reactions for this one. So the reactions are pretty simple. For this beam you have this RA, so these are the reactions, and let's just mark our regions R1 and R2 over here. And so for R1, so R1 is the region between 0 to L over 4, and R2 is the region between L over 2 to L, that is the end of the beam that you see. And let's say like the expression for the slope in this region is by theta 1 and the y is y1, and for R2 it's theta 2 and y2. So let's go ahead and write that. And also at certain distances x, so if I take in the first region, if I take say a section over here, or in region to a section over here, since we have to have two expressions for the moments to solve this problem, let's go ahead and write the expression for the moments as well from the free body diagram. So I just go ahead and draw, you can follow or you can write your own expressions and then come back and check whether you got the right answers or not. So we get these overall expressions, as you can see, for the region 1 and the region 2. Now remember, this theta 1 is dy dx for region 1, and y1 is the y for the region 1, and similarly here, right? So if you take a look at these equations that we got, so let's just mark them, maybe 1, 2, 3 and 4. You see over here we have 4 constants of integration that we need to evaluate. So we need to evaluate c1, c2 and c3 and c4. So we need 4 boundary conditions. But now if you take a look at the overall beam, what are the boundary conditions that we have? The boundary conditions that we have are that at x equals to 0, you have y equals to 0, at x equals to L also you have y equals to 0. So that helps you get 2 equations. So what is the other 2 equations which we can use? Maybe you have guessed it right. The other expressions we can use here at exactly at this particular point, at exactly L equals to 4, right? If you are coming from the region 1 over here, the theta 1 that you will get at x equals to L over 4 must be equals to the theta 1 if you're dealing with region 2. So the slope, so that is what that is the continuity of the slope. And also similarly, even if you're coming from region 1 or region 2, the value of the deflection must be the same. So the deflection is just one unique point that you have, that cannot be different from if you're coming from the left or dealing with the region 1, or if for the right if you're dealing with the region 2. So we have the expressions for the displacement continuity as the slope continuity as well. So let's just go ahead and write down the boundary conditions that we have in this problem. So out of these expressions, these ones are the easy ones from the overall beam and the support conditions that we have. So this one is a slope compatibility and this is the displacement compatibility. So now that we have these ones over here, all these expressions, so you had 4 unknowns, c1, c2, c3, c4, 4 conditions. If you go and do the algebraic thing, and then you will evaluate all the constants of integration that is there. So I'm going to go ahead and write that. You can calculate and check. So now that we have the 4 constants of integration, you can go ahead and plug in and you can essentially find the deflection and the slope anywhere, right? So this problem asks you to find the slope and the deflection at the point D. So if you substitute at x equals to L over 4 in any of the expressions that you have over here, what you will essentially get are these values. So these are the values for the theta d and the yd, that is the slope and the deflection, the d that you have over here. And if you kind of try to draw the deflected shape, it would look something like this. Now one thing to note, you see that this theta d, it has a finite value, which is the value of the slope over at this particular point d that is there at this point, that is the slope. It's a negative slope, as you can see, right? And also the yd is negative, that means this point d is actually going down. Now you see that is it possible for us to tell that whether the point of d is the maximum deflection? It's not. If it was a maximum deflection, then the slope at that particular point must be equals to 0. So here the slope is not equals to 0, so theta d is not the point of maximum deflection, right? So I hope this problem overall was clear to you. So we dealt with 2 different regions within the beam, and now also you are probably starting to get a sense, a hint, that if you have multiple loads, you have multiple points of discontinuities, so you will have multiple expressions for the moments and as many, or actually twice the number of constants of integration to solve problems using this particular strategy that is there, right? Now in this one we use the 2 different regions. So we use the end conditions as 2 of the boundary conditions over here, as well as we use the slope compatibility as well as the displacement compatibility.